I am going to talk to you about deep learning for data scientists. For data scientists is the disclaimer that lets me keep this all high level. So if you came in here and you wanted to see pages of equations, you have to wait for the second part of the talk. I guess I should mention that I have my own little company, Momentix, where I do data science algorithms and machine learning stuff. So if that intersects with anything that you're interested in, or you hear anything tonight that sounds interesting, feel free to connect with me. I just enjoy meeting people and talking about their problems, and sometimes there's some interesting collaborations that come out of that. So there is a machine learning revolution, and I thought heavily about whether or not to put this slide up here like this because it's a little bold for me in presentation, but I'm convinced this is really true. How many of you have heard of deep learning? Okay, that's great. How many of you practice deep learning in an AI way? Okay, a couple of people. So deep learning has really changed the landscape of machine learning, and it's beginning to percolate down to the mainstream. So you'll see this, you see it in the press and things like that, and you'll see it in products over the next couple of years. There's a lot of enthusiasm, and tonight we're going to talk about what that means. So the first place that I really picked up on it again, I guess I heard the original papers back in the mid-2000s, was in the press, and you can see I keep a little bookmark notebook of all the deep learning articles that come out. There's probably 5 to 10 each week that interest me, and I guess from here you can tell that I'm a little biased to read Wired magazine. But these articles that I showed you are really talking about how companies are acquiring the talent and demonstrating the use cases for deep learning in their businesses. So this is Google, Yahoo, Microsoft, Facebook, other companies you haven't heard about or other companies that don't want to talk about it publicly. On the top row, you've got some famous characters. If you happen to be an AI machine learning aficionado, you might recognize some of those people. And if not, they're just pictures on a slide. And the one guy in the middle you should recognize. He actually showed up on Monday at the NIPS conference. This is what Raj was saying. He came out to talk to the deep learning workshop, spent 30 minutes with us to sort of explain Facebook's vision. And they're making a serious commitment to deep learning. They've established an AI lab. They've hired Jan LeCun and other people. They're still recruiting if you're interested. And they are really committed to transforming how they view and use their data using the very latest techniques. And this is from Mark himself, right? So he's interested. So it's a revolution that you kind of see in the press. If you go back to look at the origins of this story, where it arose and how it's evolved, these are just a couple little charts that I've pulled together. On the left, you can look at just the citations. This is a little hack, Google Scholar citation. So it didn't do anything rigorous, just keying on deep learning neural network. But you can see that it really started to pick up sometime between 06 and 08 in the Google Scholars world. 06 is a special date, so keep that in mind. And the same thing over in Google Trends, although the little red area here, which is really the trend for the keyword, the key phrase deep learning, is a little small to see. It is picking up, it's upticking. It's kind of dominated by the scale of big data, which should be falling down again here shortly before it goes back up. And so this is the publication search trends, and you can see that the publications probably lead the search trends as you would expect. And this deep learning phenomenon isn't limited to machine learners. It shows up in all kinds of domains. So if you happen to go to conferences or trade shows or industry, you may see deep learning applications in your field. They are particularly strong in areas like computer vision and speech and audio for a reason we'll talk about. And if you're interested in looking at some of the specific publications and trends that are going on, just Google for these conferences. NIPS, the Neural Information Processing Society, ICLR, the International Conference on Learning Representations, and ICML, the International Conference on Machine Learning. These are where the breaking ideas and innovations come out. Most of these have abstracts or something online. And from there, you can search the web of knowledge to find what you're looking for. It's not just people searching, it's not just academia, it's showing up in industry and products. Google, of course, is a huge contributor to the deep learning movement. They are really invested in AI and all of the associated techniques that are going to help them make a better user experience of product. And in fact, they've disclosed that they use deep learning in Android voice recognition, in Street View for maps, and in Image Plus. And the reason they use it is because it works really, really well. It's not just a fancy, it's actually worth money to them. It shows up in other products too. In particular, most speech recognition systems now are transitioning to deep learning because it significantly improves on the state of the art. You see it in translation, whether it's document translation or language translation. In documents, that's my catchphrase for all the natural language processing tasks that you'll see. And over here is an application. If you go to this YouTube video, it's really worth looking at. I had missed this until this last week when I was preparing this talk. But here Rick is giving a demonstration of a real-time English-Chinese translation system. And in this phrase, he's saying something to the effect of, I'm speaking English now, and hopefully you'll hear me speaking Chinese in my own voice, in real time. And so the engine is actually translating him, written and verbally, and rendering it in his voice. So it's pretty neat. So with all the activity, there are some epicenters that have been established from the very get-go, and they're starting to grow out. So just to give you a context of where deep learning is happening in North America, and it's not constrained to North America, there are also great labs around the world. It really kind of originated in Canada here with Jeff Hinton. And the core universities that started a lot of the research were Toronto, Montreal, Stanford, and New York University. So those are epicenters. But of course, now British Columbia has gotten into the mix, and Microsoft, Google, Yahoo, Facebook, countless other companies that you can imagine. And anybody that left off, I apologize. I was just trying to convey the point. So if you're watching this for minutes, you'll be on the next video. So deep learning is popular. It's trendy. You're reading about it. It's this revolutionary idea. At least it seems to be. And one of the ways you know it is because the people who are doing it are really calling it revolution. So what's the origin story? Where did this thing come from? Why are we doing it? You know, what's it all about? As a data scientist, how do you make sense of this? As a data scientist, one of the things that you do is you consume or contribute to machine learning products or techniques. So let's talk about this one. And I want to go back to the days before deep learning and think about the toy example of a cat detector. This kind of captures a canonical machine learning problem, which is a classifier. And the idea is we want to build some magic box called a classifier that takes a pile of images, which are inputs, and produces labels. In this case, I'm saying cats and dogs, it could be cats and rabbits, it could be cats and data scientists. There's probably a strong correlation there. So this is a kind of a common problem, and it's something that we solve every day. How many of us in the audience do classification still for their job? I mean, right? Something that you spend time on. For less than $1 million. Anybody know why I have $1 million up there? So anybody heard of the Google cat detector? So Google is really committed to AI and deep learning, and so they built this amazing cat detector. I mean, it's probably the best. It probably detects a cat better than a cat. And they built this they used 1,000 nodes, each with 16 cores, and each iteration of training the model took a week. If you run that on Amazon prices, that's like $38 trillion. But I think they just bought the hardware for $1 million. And so this was a very expensive experiment. But it's important to keep in mind, too, because $1 million is a lot of money. So it tells us two things. One, Google is really serious about using this technology. And the other thing is that we can't be Googles, probably, in our jobs, right? So we need some breakthroughs. Okay, so if you start with the detector, a very natural thing to do is go collect a pile of data, right, from your local pet store or something like that, take some photos. And you want to use this because this is how you're going to train your detector. But the problem is that labels are expensive. Label data is expensive. It takes time to acquire. It takes time to clean it. I've got to look at it. Here, you know, if I just needed 10 pictures of cats and dogs, well, shoot, you know, 5 minutes online and I've got it. But if I have 1,000 or 1,000,000 objects or things that I can't actually get pictures of, or I have to go through manually and really spend a lot of time understanding, that's a huge problem in itself. At the same time, we probably do have access to lots of pictures. We just don't know which ones are the cats and the dogs. So we're leaving a lot of data on the table. And that kind of flies against our intuition because, you know, everybody's like, big data, right? More data makes it better, which isn't always true, but in our case, it's going to be true. So this is a challenge, and it faces us today still, but it was really acute before the ideas of deep learning came out. The other challenge is features. So how many people have face feature engineering. You know, how do I take this pile of data and make something out of it, right? That's between collecting data and manipulating it and doing features to manipulate it, that's arguably 80% of a data scientist's job or a machine learning researcher's job, right? And we don't scale, right? It takes how many years? About 15 years, or for me, 10 years in tech to get a PhD. So it takes a long time to create a machine learning data scientist. So here I'm just showing how we would do features. For those of you who haven't seen this kind of thing before, you know, if we have an image of a little kitten or something like that, a little mad kitten, that comes to us as a pile of numbers which represent pixel values, which are the intensities in the image. And we generally can't do much with the pixels, so it's a lot of data and it's not necessarily a good representation of the image, so we want to transform it. That's the process of extracting features. One thing we could do that's really silly is we could just do a histogram of pixels that are closer to being black versus white. So if I look in this image, it might look like that. That's probably not very informative of what a cat is versus something else, right? Because I could imagine different backgrounds and things. Another thing I can do is I can spend 10 years like David Lowe did and come up with this amazing psychovisual inspired feature called SIFT, which goes through an image and finds key points and then extracts some features based on the key points. So this is kind of scale and rotation and shift invariant, things like that. All the great properties of the feature for 10 years, you'd expect that. And then that's 10 years to come up with it, and it's probably a year for someone who doesn't know about it to go read about how to do it correctly. At the end of the day, what we're trying to do is take a big pile of numbers and reduce it to another pile of numbers that's useful. And that's features, and that's representation. Now, if you don't happen to be David Lowe and inventing your own feature, or you don't know about David Lowe's feature, your strategy is a classic one, which is to look up in the Magic Feature Dictionary, which really amounts to reading blogs and journal articles to find what other people have done, and try it out on your problem until the numbers work. Right? How many have done that? Translate features. And these are just some different features. You know, a lot of times you end up creating some sort of hybridized, personalized, something you wouldn't want to share with the world kind of solution. So this is where we stand in 1.0 CAD detector before deep learning. And everything in the left box is something that requires a lot of human intervention or is expensive actually in cost in other ways. And this, like we said, this doesn't scale because each time through the loop of exploring models or coming up with ideas, I mean, we're inventing. You know, we're having to manually review all this data. This isn't really automated in a great way. Of course, we do try, but it's limited. And this is what we talk about, the box on the right. Because, you know, my classifier is better than your classifier. I know support vector machines, ooh, I want a capital contest with random forests. So we like to talk about the techniques and how great they are because they eke out little incremental gains on small data sets. But the problem we're not solving is this big workflow and wasted data and feature engineering problem. So let's go back and look at the challenges that we face and see, you know, maybe we should look at this a little more seriously. The first one, how good is it to have more data? Because maybe that's a cheap way to bootstrap ourselves to something better. And in fact, it is. So that's what this chart over here shows. This is an experiment by some linguists studying disambiguation of the word to. So they want to understand if it's to TO, to the store, or to TWO, to people, things like that. And what they've done is they've taken a collection of classifiers. It doesn't matter what they are. This is a little dated because it's 2001. And they've run this collection of classifiers on data sets, training data sets that range from 1 million to 1 billion words. Okay, so on the left-hand side, we train on 1 million words, and then we go up to 1 billion words. And if we look at what happens as we go up, we see something pretty interesting. In the beginning, it kind of matters that my classifier is better than yours. But by the end, unless you really pick kind of the wrong one, even then it's not that wrong, it doesn't matter at all. Right? So what we're seeing here is this huge lift from 82.5% to 97.5% accuracy on the test set, just by having more data. Not just a little more data, orders of magnitude more data, right? But we might have orders of magnitude more data. So the punchline here is that more data dominates better techniques with an asterisk. Dominates meaning that if you had a choice between acquiring 10,000 times more data points or hiring 10 times more PhDs with all the fancy stuff, you're probably going to be better off buying the data. Okay? You have to work out the economics, but you're going to get better performance. The asterisk means that, of course, you have to have the right kind of data, and you still have to have good features. So if you're predicting a presidential election and you're asking if you like pepperoni or mushrooms on your pizza, it doesn't matter how much you have, right? you're not going to do very well. But assuming that you have some informative information, informative features, then more data is a good strategy. And we often have lots of data, especially now in the connected world, where we can obtain it. We just don't have the labels. So again, we're back to this problem. The labels are expensive. We have all this unstructured and labeled data. I say unstructured in there for the data, guys. So we're thinking, okay, this more data is a good idea. What if we had a way to use all this unlabeled data? What if there was somebody who was going to come along and just crack this problem right open in 2006? So file that away. The other side of the coin is the impact of features. And so intuitively know that features are good. Can't prove it with the same kind of study that I do with the data, or at least I couldn't find it in an hour of Googling. But features are critical to success. Again, to the pizza example for polling for presidential elections, not a lot of information on who's going to be elected based on your pizza preference, probably. But if you have something, a little more informative, like a political party you're affiliated with, how you voted in the past, demographics, things like that, that's more important. So good features are worth more than good data, but they're really hard to generate. In practice, in fact, I don't even know. I don't think there's a way that I've ever heard, a codified recipe way to go about generating features on your own. So if I give you a data set, so you go to the moon and you measure something that nobody's ever measured before with some alien artifact, and you've got to come up with features, there's no playbook for how you do that except visualize, explore, try to make an analogy of something else. It's a very creative process that takes a lot of time. And because of that, often we don't go pretty deep in features. We look for something like, does a cat have a tail? Is it orange? Right? We're not thinking about, does a cat have a tail and 4 legs? Does a cat have a tail and 4 legs and, it's on Earth? We don't compose these bigger structures of features because we're trying to get the low-hanging fruit. And the features are domain-specific, so that takes a lot of time because you have to go talk to all those annoying business people and figure out what they're doing, right? And they have to talk to you. Well, they usually just talk. So the other questions coming to our mind, aside from more data, is, wow, wouldn't it be great if the same genius person could invent a way that we could automatically generate our features? So we don't have to spend all this time. We may still spend the time because we're getting paid and we look like we're doing something, but in the background we've got this magic feature machine. So this is really what we want, CAD Detector 2.0. We want to take a lot of data, and it's just bountiful. All the pictures that I can think of, maybe even not of cats, I don't know, the kitchen sink, pizza preferences, whatever. Some of it I'm going to have labels for. I'm going to know that some of these pictures are cats. Raj probably has a collection of cat photos. But in general, I don't have to have that. I really just want to be able to dump data in the system. I'm going to wire a box up to some data source and run. And then the box needs to do everything. The box needs to take care of this features problem because we know that you can't learn on just raw data. There has to be some sort of representation. But it's going to figure that out. And it's going to pick the best algorithm or be the best algorithm. And I'm going to get the answers and we're going to do a startup and $20, right? And this is an end-to-end processing unit for classifiers, regression, or detection, things like that. How many of you guys have this right now? If you do, I want to join your startup. Okay, so this is the intuition. Those two ideas are the intuition for deep nets. I say deep nets, really I should probably not confuse deep networks with deep learning. Those are different terms. We'll see. But for right now, it's synonymous. This is a borrowed slide. This is kind of similar to what we were showing with the cat. We have an image of a car, and what we want to do to go from this box, which is the magic box, we want to think about this. We want to come up with these modules that we can stack in a cascade. And each module's job is to say, well, what did I just look at, and how can I represent that in some feature-ish kind of way? And if I stack these in this cascade or this hierarchy, then my hypothesis is that eventually I'm going to have a representation of this car image that is just easy-pleasy to classify. And along the way, I'm going to get a side benefit of these intermediate representations. And then at the end, I'm going to do what I've always done and just do some sort of classifier or something. Okay? And this is what we're seeing here. This car processing through these stages, the fact that I have many different layers of feature abstraction that build successively, that's the deep. That means that I have sort of a deep or hierarchical representation. I'll show you in the next slide. And at each output of this feature extraction, I'm learning a representation of how to decompose these images. So the car images and everything that else that went into train this first layer learned about edges. And you'll see these edge detectors, oriented edge detectors in a lot of deep learning literature. Of course, how many of you guys have some neuroscience kind of background or something like that? So why do I see edges? Because that's what the brain does. The very first stages of processing the visual system, you have oriented edge detectors. And this deep learning type of system is learning on its own to discover edges from pixel values. Hasn't been told about edges at all. They just figured that out from looking at a heck of a lot of images. And then as you go up, you get higher representations. Because this was a car-ish task, you're probably learning parts of cars. And then, so edges can be used to build parts of cars, edges and corners, and then parts of cars can be used to build, sections of cars, and then cars and parking lots and so on. So I have this deep hierarchical representation, all right? And that's the intuition. And this isn't new. The intuition for the deep networks has probably been around since the birth of AI, because people have known a lot more about how the brain works, neuroscience-wise and cognitively, than we've been able to match machine learning. But being able to do this is new, really pretty new, and still exploding. So here's just another example of a feature hierarchy, just to get the point across. So if I have these pictures of heads or faces, I say heads because I have to have a hierarchy, so this is my root node. So heads as what? Well, at the lowest level, again, edges, and this is real data. It wasn't probably trained on these images. But I start to have edges, and then edges compose parts, and then parts compose faces. And I get this really nice representation, and this is really doing feature engineering for us, right? I don't know if we could do this as individuals, certainly not in the same amount of time. So there was a breakthrough. All these ideas have been gelling and circulating around, and Jeffrey Hinton here, who is a professor of computer science at the University of Toronto, has been doing neural networks for, I guess, at least since 1985, because I saw that date way before then. He published this paper, Fast Learning Algorithm for Deep Elite Networks, and basically split time. Because before, we knew about these ideas, but we had no way of being able to do it. And after, we have some new tools and techniques that we can actually use. That was one of the big contributions, in my opinion, in this paper, is that it actually worked, and he demonstrated it. It wasn't just a proof to go behind it or the idea, he actually bundled it all together. And so it's kind of rare for us, at least in what I've seen, to be able to point to a single point of breakthrough in a field. But I think everybody pretty much universally agrees that this is the herald of deep elite networks. Whether he's the only person or not, certainly he stands on the shoulders of giants. There's work that suggested some of this stuff before, and many people who were working at the same time. But this is the one that gets the credit for whatever reason. So this is kind of the nutshell of this paper, very high level. Deep elite networks. He started by looking at a classic computer vision problem, which is classifying characters from the MNIST data set. Many of you guys have heard of that. It's a really boring data set. It's really easy too. Here's a little secret for you. Everything works at like 96% accuracy. Okay? A blind relative can point and get 96% accuracy on this data set. But it has 60,000 training images and 10,000 test images and an infinity of papers published on it. So it's not just a small problem, it's smallish, and it's something we can understand visually. So he took the NIST data set, and he posited this architecture for a deep elite network, which we'll go through in later slides. But you can see that what he's doing is, each of these images is a 28 by 28 pixel image, and he feeds this into a couple of neural network layers that have 500 units each. And these neural network layers are unsupervised, meaning that they are going to take their inputs and they're going to learn representation of the inputs. I don't tell them what it's supposed to be. And I do that for the first layer, and I do that for the second layer, and then he stopped there. That's a good question. Why would you stop? Why is it 500? Why is it 2,000? Why is it 10? Those are all great questions. But high level, he stops with a couple of representational layers, he adds this classifier layer on top that says, okay, when you get up here, you kind of have an idea of whatever's going to make a 1 is a 1. You learn that. That's what those outputs are. And so I'm going to match it to the labels telling you if something is a 1 or not. And you're going to do a traditional classification. So this process of going up the stack and training these units is called generative pre-training, or unsupervised pre-training. And so this is kind of important, because people had thought of this idea before in these architectures, but they just couldn't get it to work out. It just wouldn't work right when you got to the top. And there's some algorithmic details that kind of, the current thinking is that you have to get close to what a good representation is to be able to finish off that classification stage. Right? And then for the results, an abbreviated table of something that must be 1 million pages by now. DBN pre-train, which is what I'm calling this thing. So this is a deep belief network with pre-training. Got a test error of 1.25%. Not bad. Comparing apples to apples, the next best thing was the support vector machine with some crazy parameters that have been tuned. But you know, if you take your mom and you show her what the KNN is one Saturday, the worst you can do is 4 or 5%. So again, not very challenging benchmark. People, I guess the challenge now is if you're a hardcore guy and you really want to beat the heck out of this, you know, the current state of the art is 0.23%, which means they make 23 errors out of all 10,000 test images. And if you were to look at these images and the errors, that's better than you can do. They don't actually look right. In fact, I mean, how would we even know the labels are right? So, but, you know, if somebody's learning the labeler. So what are the key ideas that we've synthesized from Hinton's paper and from the observations that we've made by working on this over time? The first one is we want to learn features from data because it can be automatic and we can use all the data. So that's a good idea, and it seems like, you know, check, PBNs do that. The second is that, well, this deep architecture idea is really curious, so certainly worth looking at. Not everything is well represented as a hierarchy, but it turns out empirically that all the things that we tried it on, speech, language, image, sensor motor, video, they seem to be really well represented with these hierarchies. So, you know, kudos to empirical science. And they give us a representation so we can draw, you know, nice little intermediate views of what's going on as our architecture learns something. They're computationally efficient relative to not having hierarchies, sometimes. So there's some theorems that say that the expressive power that you need to capture a concept it shrinks exponentially by the number of layers you have under some constraints. So this is why we want deep hierarchy. You can basically cut down the number of operations you have to do in addition to getting those benefits. And then something we won't really talk about, but there's some shared statistics aspects, so it just kind of helps us build a better learner. The other key idea, a practical training method. So what stopped us from doing deep networks or deep learning in the past was that we just didn't have a way to train the thing other than maybe randomly guessing, which didn't work very well. And then I like the fact that at the time it was the state of the art, and it worked, even if it wasn't the most glamorous problem in the world. So it definitely showed that we had some chops. All right, so armed with reading this paper, if we go back in our time machine, 2006, and we say, hey, let's look at that cat detector again, what should we be doing? Well, let's start with more data, right? We said, hey, more data is good. So let's take all the data we can scrape off of Google Images and Flickr and Facebook and everything else. Doesn't matter what they are, right? Unlabeled images, and we are going to feed that into our magic deep learning network. And it's going to automatically learn this hierarchical representation of what makes images. Okay? Okay. An asterisk in there. And then we can also throw in a few cats. And by a few cats, I literally mean just a few cats. I'll show you a result later where you might need only 5 or 10 labeled instances of the class you're interested in. So, you know, talk about being able to tackle class and balance problems and things like that. This is amazing. When I do that, I end up with the Magic Cat 2.0 detector, which perfectly describes cats. Or I could go sell it to Google for $1 million, $990,000, something like that. Okay, so that paper really introduced the key concepts for deep learning. And so, in a nutshell, the first point that I want to make about deep learning is architectures versus features. So before we had deep learning, we spent a lot of time trying to engineer what features there were. Now I'm going to let the machine take care of the features, but I need to think of something else. I didn't completely get rid of the problem. I have to think of the architecture of the machine. I have to tell you, what kind of neural network, for instance, this is, how many layers it has, how many nodes. So that's sort of like the feature problem, except it's a lot more tractable because I don't have to invent as much as I would for features. So I can explore that space a lot more quickly. And in fact, I even have some ways to help do that in an automated fashion. The other key idea is deep versus shallow. So deep features, they seem to work really, really well. And people have done studies to show that it's not the more data or the neural network being something different than the support vector machine. It's the fact that the features are deep, they're better. So there's some power in having the right features. Automatic features, that's just great, right? Because now I don't have to come up with all these ideas or go read all these old papers. But automatic with an asterisk because, again, it's not completely automatic. I still have to think of the architecture, and I do have to still do a little bit of data prep, and I do have to still explore things. And by no means are we building perfect features these days. That's still an open research area. They're just better than what you would get with a bunch of undergrads who don't care about your data science class who are trying to come up with features. Lots of data versus the best technique. This is one that we might not like to hear as a machine learning or data science researcher because we're invested in our tools and what we learn, right? We put a lot of time to acquire that knowledge, and if you bastardize this idea, it becomes big data solves everything, right? Well, that's not the case because remember, we still have to go figure out this architecture stuff and we have to tune it and watch it. So there's still a lot of expertise. It's just we're more productive because our efforts are spent on a different focus. Compute versus human intensive. So by no means is deep learning cheap, right? Google, a week to run a model on 1,000 nodes. You can't win a Kappa contest like that unless you're using Google's labs. Yep. But compute is feasible. If you had the next great idea and you wanted to do that, you could do it. You could run it in a week. But you can't match that in human time. Who knows how long? It's unbounded how long it will take you to come up with good features and stuff. So that cycle that we go through the workflow, collecting data, massaging it, coming up with features, building models, testing, and going all the way back, that gets shrunk and changed a little bit. And it's state of the art. And I don't just mean state of the art on Hinson's paper in 2006. If you go to a conference like NIPS, where we had 1,900 people who were applying all kinds of machine learning techniques, every poster, as far as the eye can see, is deep learning wins, deep learning wins, deep learning wins, deep learning wins, deep learning wins. And it's not just on toy problems. It's on real industrial problems, real scales, real dollars, real contests. So this is very different than, say, neural networks in the 80s originally, or support vector machines and statistical machine learning in the 90s, random forests, people got into that. These are all great ideas that made improvements, and they pointed to principles that could help us. This is really game-changing, because it really dominates these other techniques and performance for the things it can be applied to. So how does it work? It's kind of complicated. I haven't given a neural network lecture in forever, so I'm just going to try this, and you guys tell me. I'll look at your faces, and I'll see if this is going okay. I'll be a confused audience member detector. Okay, so this is a neuron. It's an artificial neuron. It's my model of a neuron. It represents, mathematically, kind of at a high level, what's going on maybe in your brain, based on neuroscience studies. The neuron is the node, in green. And its job is to map inputs to an output. So it's just a little math function, right? In some form, it's kind of like a little regression. And one of the inputs has a special name called a bias. And this is a 1 always, but we let the weight vary so that it can be a free parameter for a model. The other inputs are the z's, and these are just numbers that come into the system from wherever we get them. And associated with each edge going into or out of a neuron, unless we specify otherwise, is a weight. So the idea is that we take all of the inputs to a neuron, sum them up, and produce an output, y, which is some nonlinear function of the inputs. And this is kind of what happens in your real neurons. If you get stimuli from all types of different sources, then that's going to produce a big stimuli, but it's not a linear relationship. So that's what we're saying, right? When we have a lot of stimuli, our x is big, and then we output something that's not linearly related to x. And here are two functions that we have. We call these activation functions, and they describe how much you turn on a neuron based on its inputs. And these are just curves. So you just literally plug in the values and see what they are. The sigmoid, very common and popular, bounded between 0 and 1. So if you go out here forever, it's 1. That's kind of handy too, because it means that you don't ever go out of bounds in your data. Same thing with a hyperbolic tangent, except instead of 0, 1 is minus 1, 1. And there are a whole host of other activations. You can invent your own, right? And there's actually sort of, I say, urban theory or urban knowledge about how you invent these. But there are a couple that are popular. Those are two. If we take a collection of neurons and we put them together in something that looks like this, we have a Wikipedia art entry under the topic neural network. This is a feed-forward neural network. And so what happens is, the way I like to think of it is, it's a data flow graph. It computes from the bottom, data comes into this network. This is just a graphical representation of, you could represent it as a big math function, right? And the data flows through this network, being transformed each step of the way until I get outputs. This is kind of the 1985 style neural network. They're not bad. We have lights. So, the 1985 style neural network is not bad. You have inputs, hidden layer, and output layer, just to give names to it. Now, when I see graphs like this that are computing something, it always scares me. So I like to see an example. How many of you have seen a neural network before, by the way? So maybe 30% of the audience. So some of you guys might be scared of this right now. So let's think about this neural network as solving the cat-dog detector problem again. In the cat-dog detector problem, we might have some features: weight, number of teeth, number of whiskers. These are things that I measured for cats and dogs. And I want to be able to generate a label for cat and a label for dog. So how does this work? I measure an animal, and I get some numbers, and those are my inputs. I multiply those inputs by all the weights to propagate them up. I'm feeding them forward to the next layer in the neural network. That neural network takes the sum of all of its inputs and fires. Green might be, it's really happy. Red might be, I don't really think it's this. I'm not excited. That's the output. I do the same thing going forward up to the next layer of the network, and so on until I get to the final output layer. And so what we're doing here is we're computing these inputs. We're computing outputs from these inputs just like we would in any other classifier regression system. It just looks a little different. And the trick, or the question here, is how do we get all the weights for this network, right? And so that's how you train neural networks. That's the problem to training neural networks. The answer was established a long time ago, and the consensus is it's a pretty good answer because it works really well. It's not that hard to show mathematically, but I'll try to show it graphically instead. We do backpropagation. So for each instance that we give to the network, we have, because this is supervised training, we have the real answer. So in this example we just worked, maybe this is really a cat, so that's a 1, and it's not a dog, so that's a 0. Right? So that's the true values that we have, and from that we compute the error at each node. So dog was supposed to be a 0, and maybe it's not quite a 0, so there's some error there. And we're going to use that error to update our weights. And that's our strategy. We're going to show a sample, we're going to look at what the error was, we're going to go back and adjust the weights, and we're going to find somebody who can prove this is going to converge in some great way. And what we're really doing when we're adjusting the weights is we are taking the error at any given node and we're distributing it proportionally backwards according to the contribution of the error that that path made. And as we push it backwards, we're going to proportionally adjust the weights in the right way. Okay. So if you pick this, if you set all the parameters right, it works. It's great. And that was this is where we've been since 1985 with neural networks. From my view, probably not from neural network researchers' view. In this case, we roll that out at the beginning of the error. So that's a feed-forward neural network. It's not the only network. This is like, think of this as a module. This is a function. This is a building block. And we have other types of building blocks. And so there's two that are kind of interesting. They've been around for a really long time too, at least since the 80s. But these are almost necessary now to do deep learning. These aren't the only other architectures. There's a handful you can imagine inventing your own. The top is what we call a restricted Boltzmann machine. And what makes it different is that, first of all, it's not directed. So it's a little bit of a problem. We don't have a direction per se. But the big difference is that there's no outputs. So when we have this kind of architecture, we're not trying to correct what the right answer should be. We're just trying to model the data. That's all. Remember we said we need these feature layers, something that could represent data in some higher abstraction. And it turns out this is one of those magic boxes. Programmatically, or operationally, it differs a little bit from the other networks in a couple other ways. The actual activation, these neurons firing, it's random, it's stochastic. So when I run training data through it, I have to simulate a random number to decide I'm going to turn that neuron on. So this is a nice little twist. It's useful. The other thing is we think about these networks in terms of energy landscapes, and the energy landscape sort of tells us how misconfigured this is in terms of representing the data. And our goal is to find the minimum energy, and if we find the minimum energy state, then we correctly describe the probability distribution of our data. And the energy connection actually goes back to physics, which is why we have Boltzmann in here, so if you're really math savvy, then you can go read about that. Another one we have is the autoencoder down the bottom. We really only need kind of the hidden layer here, as I've shown it. But I'm trying to show you what's going on. On the autoencoder, the strategy is I want to represent data with less nodes than number of data points. Right? And the idea is that if I have a representation, this hidden layer, that is smaller in some sense than the input, then I'm going to be forced to learn something about that data that's a good representation. It's robust, it's generalized, it's not going to overfit, etc. So autoencoders are a deterministic way to do unsupervised learning. And the strategy is I give it an input, and then I predict an output, I look at the error, and I take the weights, and I iterate and iterate to convergence. And so what I'm really doing is an approximation of the input, driven by my reconstruction error. So, and both of these are useful. It's not clear that either of these really is learning some sort of universal features or things we want, but they're definitely learning distributions, probabilities, and reconstructions and things, so those can be useful, and they work. So just to kind of show you what happens, you remember we had those MNIST digits, those nice little grayscale images. If I run those through a restricted Boltzmann machine, or a denoising autoencoder, the denoising is just an improvement upon the autoencoder to make it more robust. And then I look at those those hidden layer networks. So these hidden layers are like latent factors that they model what the data should be like. Those hidden layers tell me what the data should be like. That's what I'm learning. If I visualize those, these are some examples that you can get. These are actually from the Python Piano demos, so you can go find these online. So you can see that it's kind of learning some things like, where most of the activation of the image is in the center, and there's kind of a 2 there and a 6, so these little squirrels must be popular in some way, and maybe there's some strokes down the middle or something. So as for a first layer feature, it's kind of sensible. And on the denoising autoencoder, I can't say quite the same thing, but it's sensible. And they're different, and I'm not sure that there's really a preference. It depends on your task, which one of these you would use. So I can't really say that this is learning something better than the other. But if you go read the papers, some labs like the autoencoders and some like the restricted Boltzmann machines. So we have these RBMs, restricted Boltzmann machines, which are these magic little, small, shallow neural networks that give us features. You give it some inputs, and it learns better representation of the data. And we have some example of somebody doing this in the past, showing us that if we stack these things together, we can learn really good representations. So we kind of have a recipe now for how to go do our own deep belief network. And so we start maybe with the unsupervised part. And we decide that we're going to have 3 layers features and some input data. And our recipe is simple. We load up lots of data, and we collect some labels, and we set the labels aside for a minute. And then, stage-wise, greedily and successively, we train each of these RVMs. Right? At the end, we put the classifier, the final top layer on there. We wire up the labels and say, well, this is what you should have learned. And we tweak the whole network so that it learns that. So when we're going through these stage-wise progressions, we're kind of learning a space, a feature representation that describes our images, and then we're fine-tuning it with this final layer, saying, okay, you kind of have a representation of these images, and this is what you need, to start learning this pattern. This needs to be a 1, this needs to be a 2, something like that. And that's deep learning, but of course, that was deep learning circa 2006 now for Data Science 101, and we only have an hour. So there are a lot of other very, very important things that I've left out of this, which I'll just talk about briefly, so that you get a flavor of how you go from this kind of idea to the next level of improvement. So the first thing is dropout or regularization. So when you're building these networks, every little weight in the network is a parameter, and you might have millions, I don't know if there's trillions now, of parameters. You might have thousands of data instances. So this is statistician hell, right? Because you're trying to learn models that are really overspecified. So you've got to have a strategy to keep you from overtraining or cheating or whatever you call it. And regularization is what we call it here. And dropout is a recent technique for doing that. And I can't describe it actually. In dropout, you basically do what we described before in training, but at each time you hit a layer, you randomly set some fraction, like half, the weights to 0. And for those of you who are interested, what that really does is model averaging. Dropout is to neural networks what ensembles are to trees. This is our version of random forest, except maybe even more. Another thing you can do is you can change those activation functions. Even though the sigmoid and the hyperbolic tangent are nice, they have some nice derivative properties, nice range compression or limits, it turns out that they're not the best performing for theoretical and empirical reasons. So you might want to do something simpler, and the current flavor of the day is the rectified linear unit, which actually is simpler, so you can go look it up on the computer or something like that. I'm not even talking about convolutional networks because of the word convolution, which I'd have to describe, which is maybe not hard, but I don't know if everybody's seen it. But convolutional networks are definitely the flavor of the day for beating up on all these competitions. So if you dream of winning that $1,000 Kaggle contest for 900 hours of your work, you need to go spend a couple of years, get a PhD understanding convolutional networks, and you're good to go. But seriously, convolutional networks are really powerful, and they're definitely worth looking at. They are the state of the art in image and speech for sure. We're going to talk about hyperparameters, so all the little magic numbers that I have to use to make this thing work. How many nodes do I have? How many layers? How many epochs do I do? How do I train? Any sort of parameter that I have to set in the system, and there are a lot. They're little knobs. There are little opportunities for me to make mistakes or have a non-principled way to build these networks. So that's actually, to me, that's a big problem. In fact, I think everybody agrees this is an open issue. So we're not quite to hook the deep learning network up to the data and run it. I didn't show you, but it's not just neural networks. So instead of each of those restricted Boltzmann machine layers, you can plug in your own favorite algorithm that's unsupervised. K-means, KBCA, ICA, do some transformations like that, stack them up, put a classifier on the top, and you can get really good results. In fact, I think K-means leads in one of these little contests. So these are familiar algorithms that you get to reuse instead of doing deep learning. And the last one might be the biggest. There's a lot of practical issues. So there's sort of two dimensions for this. The first is you can't really play with this stuff unless you have a GPU and good code. It takes, if you go walk around NIPS and people talk about, oh yeah, I like your poster, that's great work, good stuff. Yeah, it only took me about 6 months to run that model. Right? 6 months. So, months or weeks are common, days, of course. But you really, if you want to do this, you have to be able to iterate faster than that, and GPU helps you. It can give you an order of magnitude speed up, or if you're a GPU wizard, if you came from NVIDIA and happen to be really good, you could probably go 2 orders of magnitude, which is expensive. And the other practical issues are all those magic numbers that we talked about.
And if that's the case, you should get in contact.
Yeah, actually, if you can speed up more than 100-fold, just call me, I'll help you do something with it. So the magic numbers, there's kind of an acknowledgement that there is an oral tradition of passing knowledge down through this neural network community. And the tradition is sharing what these magic numbers and recipes for success are. Maybe you're just sitting next to your cubemate or something. Well, sitting next to my cubemate didn't matter to me when I was getting an electrical computer engineering degree because that's all worked out. But this stuff is all, kind of smoke and mirrors, ooh and do. So if you don't have a connection in one of these groups or have a lot of time, you could be spinning the wheels. So that's kind of the nutshell. Let's look at a couple of applications. The NIPS conference ran from this year, from Thursday through Tuesday. Full sessions, so from about 7 in the morning to midnight, because they do demos and posters and everything. It's literally, on a full day, you would be booked 16 hours. And over 1,900 researchers presenting on this stuff. And so you can imagine there are so many applications that are so cool. It's like looking in the future. I don't know that I really captured any of these here because I couldn't, rip off the photos, the images from the papers that are on up yet. So I'll give you older cool stuff maybe. The first one is, I feel compelled to put it in here because it's talked about everywhere. And it's for ImageNet. ImageNet is a challenge to classify images. There's a lot of images, millions of images, and there's lots of classes, so over 1,000 classes. Dogs, cats, rabbits, letters, echinacea, blah, blah, blah. And the way they pose the problem is, build a classifier on this image data set, and we'll score you 2 ways. 1, we'll score you if you get it right. 2, we'll score you if you get in the top 5. So you, at any given time that I'm going to test you, I say, here's an image, you give me back your number 1 answer and your top 5 answers. And I score you in those 2 ways. And the top 5 answers just kind of recognizing that some of these things are ambiguous and some of them may have multiple labels in the same scene. So this is an output of the system, and this is from the system by Krzyzewski and Hinton and others that won this contest in 2012, and they published it. And so you can see, like here, we have a lens cap as the label for this image, and it gave you reflex camera, Polaroid camera, pencil sharp, etc. So it might not have gotten it right, but it was certainly very sensible, and maybe right by some arguments, right? Here's a clear example of abacus, and so that's the correct label. Planetariums, state players. So you can see that, in general, it's recognizing these images, right? Over here, you've got a hen, clearly says it's a hen, a tiger. And this is amazing to me, that this works so well and so quickly. And apparently it's amazing to Google, too, because they bought the company anyway. And this is what actually is powering image search for Google+. They not only got the company, they also got Jeffrey Hinton and a couple of his students, so an acqui-hire. Love to understand pays for this. Probably more than $1 million. This is just this is the photographer we like in the pretty picture. So in biomedical imaging, a lot of times you'll have images you need to segment, and segmentation is hard because you can imagine where you draw the boundaries. And this is an application of deep networks for neuronal membrane segmentation, and just qualitatively to us, this is a really good job of segmenting the image. So you can count cells. So if you have a child or a relative who's in school studying biology, you want a really cool science fair project, go pull down this paper, take a couple of slides, and boom, you got a scholarship for your kid. This was the first time I saw this is the intro section at NIPS. Rob Fergus, who's at NYU, who also got hired by Facebook, so he's making a lot of money to put his name to this new lab. Showed lots of pretty pictures. What struck me about this one is the Caltech 256 data set. It's an object recognition data set. And I think there's about 1 million images here too. And so Rob's group trained Deep Convolutional Network on 1 million, I think 1.3 million images from this data set and elsewhere. So the strategy we saw in the very beginning, just feed a lot of images to sort of pre-train what makes good images. And then what we're showing here is how many additional training instances do you need to get a certain performance. So if I want to recognize fuzzy bears, how many fuzzy bears do I have to show you to get a certain performance? And what's fascinating is that with only 6 examples of a class, he beats the state of the art. Think about that. I mean, you can go to Flickr or Google or wherever you can web scrape most efficiently. It's Corel CEs. For some of you, maybe Corel 3.5 copies. You can load up all of your images, train something that understands what images are, and then just give it a few examples, and it'll learn. You'll have a state-of-the-art detector. That's kind of the vision, right? I don't know if you made anything off that. I went to grad school back when speech was cool. I don't know if it's really cool anymore.
Hey, it's cool.
It's cool. Pindrop. Pindrop's speech in Fallout, so that's like really cool. So for those of you who don't know, when you record speech, you're recording time series. This is really compressed because this is several seconds, and the characteristics of speech signals are really best displayed on millisecond levels. But you can sort of see from the envelopes what's going on. This is the phrase, you can, for example, present significant university-wide issues to the Senate. And this keeps a lot of linguists in business because they go through and listen to this and they mark it up. Oh, this is when we said he, this is when we said the, etc. So this is a time series, and then we don't usually think about analyzing time series in the time domain. We have a representation. This is independent of deep neural networks now, by the way. This is just good math. We transform this to frequency domain. The spectrogram is one such a time frequency representation. What we do is we take this little window, like this red region, so there's a little finite amount of time in there, and we slide this window across the speech signal, and every time we move it, we convert mathematically the numbers here into a vector of frequencies. And so that tells us the frequency content over time of the speech signal. And things that are significant about that are that the human vocal tract has these formant frequencies, like I'm painting here, these bands. These are the resonances of your vocal tract system. And they're kind of unique to you, and how you speak is unique. And all kinds of things, interesting things show up in speech. Gender, age a little bit, sex, stress. You'd be surprised where you're from. But anyway, so one thing that we like to do in a speech problem as a core thing is recognize phonemes, which are these little bits of the sounds of the words, he, ka, things like that, so that we can string those together and understand what's being said. So phonemes are kind of an atomic unit in speech theory we want to look for. And this is Hong-Kak Lee, who basically he started with unsupervised deep networks. So all he wanted to do was feed the data in to a convolutional network that had a couple of layers and see what the features look like. That's what we're looking like for images. And what he found was that he detected phonemes. That's where the features are learned. In fact, he detected almost epsilon close to the state of the art. I mean, speech has been around, studying speech signal processing, from the 60s at least. And so there's been a lot of work in optimizing that. And so this just sort of worked. And this is, again, a spectrogram, and it's colorized, and it's just showing you, like this little band here is something, whatever that phoneme is, and here's another one, and there's another one. And the thing to take away from this is that sensibly, these look like they could be atomic units of a spectrogram. And then he also did a couple other experiments, speaker identification, phoneme classification, and in traditional deep neural network fashion, or actually in traditional academic publishing fashion, you beat up on algorithms. So in this case, I think this is actually the real deal. And even though 80.3% versus 79.2% is small, and we don't even know if it's statistically significant in some way, this is academically significant because these little margins get harder and harder to improve upon. And usually those small improvements they sort of foreshadow better understandings of systems. There's a long list of other techniques. Kaggle, in 2012, Jeffrey Hinton's students decided to start beating up on Kaggle. No real machine learning academician types had publicly said they were working on these because maybe they didn't want to risk it. But they absolutely crushed these two competitions. The first was molecular activation, so Merck wanted to give you some molecular data and say, predict whether this is going to target a biological system or not. And when I say crush, I mean they might be 90% accurate versus the next closest competitor might be 60 or something. Salary prediction, there's a startup that wanted to predict from textual ads in the UK what the salary would be for that. Good information for that kind of business. They crushed it there too. One I saw, Dips I love, was a system for learning Atari games, for reinforcement learning. Literally watching the image of an Atari 2600 emulator with all those great games like Breakout, and learning to play and beating humans in 3 or 4 games. Talk about some powerful stuff. I was looking for the video of that, it's not up yet. For those of you who do natural language processing, NLP, all the standard stuff like chunking, name recognition, parsing, etc., that's been done, is being done, state-of-the-art stuff. Activity recognition in video, and make sure somebody's not following with bad intentions. And of course, the bread and butter of everybody who does data science, marketing, advertising, and recommendations. Of course, it builds on that. As a conclusion, a couple of points that I want to reiterate. The first is that we have some knobs at our disposal, data, features, and techniques. And before, we might have been bottlenecked by features and focused on technique, and now we're kind of free to the features, and we're focusing on the data. And these systems are scaling huge petabytes, thousands of machines. Creating features is expensive by hand, so we're going to get away from that. And now we have these new representations, hierarchies, which for today they work, and they work well. Data is bountiful and effective, we see that lesson, and compute time is scalable, even if it's expensive. It's scalable compared to human time. So far we're winning. And then the punchline kind of is overwhelming. Deep networks are overwhelmingly the best technique when you can do it. So if you have a problem and you're interested in the research kind of point of view, go see if you can apply a deep network to it. If you can, that's where you need to spend your time. Now here's the consequence for people in the business community. Deep networks get us really close to this magic idea of just hooking up AI to a data source. So forget about domain expertise and knowledge. I mean, the holy grail of this is that I don't need to know what your business is or what the type of data is beyond the fact that it's a table or text or an image. I'm going to learn representations. I'm going to learn things on top of that. So that has a lot of consequences. If you're in the game of having domain expertise to protect your business, you should be scared. And if you're a startup and you want to enter a field, you should be excited. Lastly, the details and tricks of this are amazingly complex. Jake is going to talk a little about our experience. I bought this $10,000 server with a graphics card and 300, 400 gigs of RAM and to wire all this stuff up and spend days trying to compile code or figure out what a magic number is. It doesn't get easier until it gets easier. If you want a reference, go to deeplearning.net or you can contact me. If you're interested in deep learning and neural networks, just go ahead and connect with me. We're talking about having a training workshop in winter or spring, so think about if that's something you'd be interested in participating in. Of course, projects and consulting, but any sort of collaboration or questions. If I can help you, I will. If I can point you in the right resource, I will. All right, that's it. We have time for questions? You want to do it?
We do have time for questions.
Okay. Any questions? Yes.
I have a question about label data.
Yes.
Does deep learning require label data, or is it like as a percentage? What's it for? I don't understand that part.
Can you repeat the
Yeah,
question?
can you repeat it again?
So you said that deep learning doesn't require as much label data.
Right.
So does it require like a smaller percentage label data? Or
Yeah, the way to think about it is, the way I think about it is deep learning is a stronger learner. So if you have less labels, you can still get the same performance.
But you need some labels.
If you're trying to do supervised learning, you have to have some labeled data right now. Or you have to hand wave in a nice way.
All right, so anyone who asks a question gets a paper of t-shirt.
All right, yes. Yes, yeah.
So with the old school like backpropagation neural nets and everything, the fundamental calculation between the different nodes is basically adding and subtracting for the hardware. What's the fundamental and then differentiating or whatever?
Adding and subtracting.
For perceptrons for the old school neural networks.
Yeah.
But what information information are you actually passing on in these deep networks? Like I saw the graphs, but I guess I missed what you're actually passing through.
Yeah. So yeah, the question is the difference between old school neural networks where you're adding and subtracting values between layers and none where activating, and then what are you doing in the new networks? So I'm not sure that I'm seeing that question exactly.
So what information, what calculations, like at the smallest level, what calculations are you doing?
Okay.
So you can think about each hidden layer. Sorry, I'm not going to talk.
I'll remind him for those.
So you're reducing the amount of information. So say you went from a Gaussian to just a binary state, your hidden state. And you could have the same number of hidden layers as your visible units, so you're still reducing the information set because you're still going from this Gaussian to just a binary. And you're just trying to create little bits of information bottlenecks that kind of shape the data in other ways so that, like, because everything's going to be connected to that hidden layer on the next layer, you're learning a little bit more. You've just reduced the feature space a good bit.
If you think about the two unsupervised networks I showed you, the restricted Boltzmann machine and the autoencoder is classic mathematics. So it's still adding and subtracting and doing a nonlinear transformation to go from the input to the output. The restricted Boltzmann machine is like that, except that there's a stochastic firing. So I add, subtract, and then I sample to see if I fire. Yes.
What's the difference between deep networks and the deep networks?
Say that again. The difference between deep and deep learning. Oh, so yeah. So deep networks. I'm thinking of deep neural networks. So the layers are artificial neural networks, like we've seen. But deep learning just refers to the idea of these hierarchical feature representations. So I could, instead of having neural networks, I could plug in some other learners. Like I was telling you, go look up KPCA, and that's a way to do unsupervised features that people have done for deep learning. Do you have a question in the back? Yeah.
Yes, I did have a question. Also talking. So, of all the things that you talked about, the most nebulous to me is this idea of feasibility. It seems like this deep learning concept is a fairly high risk endeavor if you don't know the feasibility of your problem. Can you comment on the riskiness of going into this? I mean, you talk about long compute times and just general feasibility of this. And it seems like there's been a lot of application sectors to this, but I mean, moving forward, if one were to apply this, how would the kind of risk analysis go?
Yeah. So I think that's certainly true. I think the biggest risk is, kind of on the experimenter side, what skills and tools you have. Like when I ran, Jake and I were doing these experiments on the MNIST data set. You can go read on Piano. These things take, maybe 6 hours to run the CPUs and under an hour to run the TPUs. So there's definitely a risk in how much time you have. One way that I addressed that was looking at, can I learn smaller proxy networks to sample? Can I learn simpler networks that are proxies for what we're coming? So I think that's the strategy. I think you have to kind of pose a roadmap that you sort of sample the solutions you could explore and see whether you continue or not. In practice, I don't know that people are talking about the risk because everybody who's into it is really all into it, right? If you work at Google or Stanford or Facebook, in the labs they're doing this, you're doing it. And if you're getting a PhD, you're doing it. So the risk is infinite the other way. But I think you could control the risk by having toy data sets or toy problems that can give you some indication. But again, I think the experimenter has the biggest challenge in trying to practically implement these systems. And I don't know how easy that is to do for people in general. Yeah, question?
How far did you get your experiment?
On the MNIST data set? Yeah.
Repeat the question.
How far did I get on my MNIST data set? So actually, I got a result that I think I might be trying to write up and publish, which is that you can sample your data set and your architecture of networks to learn smaller problems, which are indicative of your performance if you do the full-blown thing. That's not a new idea. This was the topic of NIPS, for instance. They actually look at training over time and cross-validation polls and things, and they predict. That's something akin to what I did. It took about a week or two for me to set that up, think through it, and run it, but I wouldn't say that was, a full-time effort. Yeah, so sparse. So the autoencoders run in, like a minute or 5 minutes or something, and the restricted Boltzmann machines run in an hour hour and a half. And so my first question was, can I learn on this problem using denoising autoencoders, stacked denoising autoencoders? And if it works, will that translate to the district propulsion machine? So can I do some really good experimentation with a cheaper network? And that actually did work for me, but that was just for this thing, this problem. It's actually this goes.
One more.
All right, one more. I think I saw you in the back. But you can come back, please. Yeah.
It sounded to me as though if you're developing this layer of features from, let's say, a large data set of images, once those features are there, if you will, however they're defined, doesn't, as you apply this to different problems, isn't it a matter of just training?
Yeah, that's brilliant. And thanks for pointing that out. That was the point I wanted to make. So the question is, as we go through and study images, so imagine our cat detector, I feed it every image on Google, and I learned those feature representations of what make images. And I haven't told it that I'm interested in capturing anything. It's just learned what images are. Well, that's reusable, whether I want to detect cats, or dogs, or people, or license plates. Okay? Maybe not perfectly, but that's very important. And in fact, it goes even beyond that. The very architecture is reusable. So I told you about the Kaggle contest. There were 2 different contests. They were won by 2 different lab mates, and they basically used the same system. So this is what is, what we see with this acceleration of productivity. Instead of being able to invent features, I have this general framework, and I just have to do a little tuning to translate it to another problem. Sometimes I might have to even give you data, but there's a lot of reuse, which gives me scalability. Okay, thanks. I want to take this opportunity to introduce Jake. Jake has been working with me on this, and he's going to talk in more details about the distributed pulse machine there. No, he's going to just talk. Okay, thank you guys.
My talk is going to be way over on time. Travis was asking to push us off, but my talk was going to be actually trying to implement and help you understand how you actually estimate the 2006 Hinton paper and how you start moving past that. How many people are practitioners and actually would be interested in that sort of workshop sort of aspect? So we do have quite a few people. What I would probably add, go ahead. Do you want to do? So stay in touch, and we'll post something about a workshop for actually working through how you're going to estimate a deep leap network. We'll talk about some of the big differences, all the hyperparameters, what you can start thinking about on what matters and how you can apply these to your own problems. So stay in touch, and we'll get something posted on the meeting site.
Ladies and gentlemen, thank you very much. Andrew Gardner and Jake Smith.